In this video, we want to investigate Newton's law of cooling. Now, this is the formula for it that you can see right here. And what this formula describes is the phenomenon that if you were to take, say, a hot cup of coffee, right? Maybe you had to heat it up in the microwave or you poured a fresh brew of Joe. It's hot. If you set it on the counter in a room that has a particular ambient temperature that's got to be, at a constant, whether it's 74 degrees or 78 degrees, whatever, the temperature of the coffee is going to cool down, and it's going to try to match the temperature of the environment that it's in. This can also be manipulated to be a law of heating, so that if you were to take something out of, say, the freezer and put it on the counter, it is naturally going to start to warm up as it is matching that temperature of the environment that it's in. And so Newton's law of cooling describes what that looks like. Now, one of the things we need to understand here is that T is going to be the temperature of the environment. And this is going to be some constant, right? Now, I know that if you take a hot cup of coffee and you put it in a room, there is going to be some heat that is leaving that cup of coffee that could affect the temperature, but it's going to be a very minimal change as the environment is much bigger than that cup of coffee. And so as they're fighting, that environment's going to win out and it's going to be cooling the cup of coffee. And U naught is going to be the initial temperature of whatever the substance is, right? So K is going to be your rate. T is the time that is, like the lowercase t is, time is usually measured in minutes. So we just have to make sure you read the question so you know what it is that we're measuring. For example, we have a cup of coffee starts out at 92 degrees Celsius, okay, pretty hot. And if the air temperature in the room, let's suppose that is 20 degrees Celsius. I don't know why I'm saying Celsius. Why did I do Celsius? Here in America, we don't use Celsius. Unless you're a scientist kind of person, so then I guess you do. Okay. So the problem here says that in 4 minutes, the temperature is going to equal 85 degrees Celsius. So in 4 minutes, we've gone from 92 degrees down to 85 degrees. And the question is, when will the coffee be 60 degrees? Maybe you want a 60 degrees Celsius cup of coffee and you don't want anything hotter than that. So how long do you have to wait until it's cool enough? We might say, well, we don't have the rate. How do we figure that out? Well, we have enough information to be able to piece it together and find the rate, just like we've done in the previous problems. So we know that in the formula up above, we know that in 4 minutes of time, it is going to be 85 degrees Celsius. We know the room temperature, and we know the initial temperature. So the only thing we don't know is K. So you plug in what you know, and you figure out the thing you don't know. So this final temperature is going to be 85 degrees. The room temperature is 20 plus. Now, you're going to notice something interesting here. This U naught minus T is going to be the initial temperature, 92 minus the 20. So it's going to be 72. So it's really just the difference of those two guys. And that difference is connected to the exponential. So E raised to the K times 4 here, because we're talking about 4 minutes. Well, this is just a regular, normal exponential equation for us to solve. We're going to be applying logs here later. So let's go ahead and solve this and figure out what the K is for this particular example. All right, so first we're going to move the 20 to the other side. So long to U. 65 is equal to 72 e to the 4k. Divide both sides by 72 because we need to get rid of all the stuff that's in front of the exponential. 65 over 72 is equal to e to the 4k. And as always, let's apply natural log, which will give me 4k from the right equals the natural log of 65 over 72. finally, k is equal to the natural log of 65 over 72, all divided by 4. So let's see what k is approximately equal to when we go over to the calculator. With the natural log of 65 divided by 72, all of that is divided by 4. So k is approximately negative 0.02557. 0.2557. So that's going to be my k, which means I can now use this to come up with a function for this entire thing. So let's make sure we're not forgetting anything. So we start with our T, our environmental temperature. T is 20. We had 72 E. We now know what our K value is. And then we have times T. So this is going to be the formula that will tell us what will be the temperature of the cup of coffee for any point in time here on out. Now, you'll notice that because we have a negative power here connected to the exponential, that all of this piece right here, this is going to go to 0 as t approaches infinity, which means that eventually the cup of coffee is going to get down to 20 degrees Celsius. Okay, now this question was asking, when will the coffee be 60 degrees? Okay, well, that shouldn't be a big problem. We can just do the algebra here. So, when will our temperature be equal to 60 degrees? Well, let's plug it in. So 60 is equal to 20 plus 72 e to this number. Now we're going to solve this for t. We got to solve for k the first time so that we would have the k that connects everything together. So we subtract 20. And then we're going to divide by 72. Again, I feel like once we do one of these problems, they're all pretty much the same. There's that first hurdle that we have to get over, which is maybe finding the k or finding the initial value. But then after that, it all becomes the same. Not that I'm really complaining. It's just if we are aware of that, then it can make these problems very simple. Again, our variable is in the power. We want to undo that, so we apply the log to both sides, in particular the natural log. All right, so natural log of 40 over 72 equals that. So then t is equal to the natural log of 40 over 72 divided by negative 0.02557. Let's go to the calculator to see what this is. So natural log of 40 divided by 72. Then all of that is divided by, well, basically just the answer that we had up above, but I rounded it, so let's stick with the rounded answer. So this is approximately 23 minutes. So for this person, get the coffee down to 60 degrees so that they don't maybe burn their tongue. They're going to have to wait 23 minutes. Okay, so we found the k value, and then we use that to find out what the what time it would take for it to get down to 60 degrees. So let's go to the graphing calculator, and let's have it do some of this extra work for us. So we're going to graph our function, which is 20 plus 72 e to the negative 0.02557 x. Okay, so let's see. let's choose a good window. So 0 is going to be the minimum. We were getting up to, what do we say there, 23 minutes? Let's actually take this out to 150 minutes to see what the cooling effect is. X scale, let's make that 10. The Y minimum, now we should know what this is. The Y minimum should be 20, because that's the room temperature. And the Y max, it was 92. And let's see what this graph looks like. Yeah, so we can definitely tell that we are cooling off. And it's going to start to flatten out here. Yeah. Okay. Now for the other piece we had, it was, when is it going to equal 60 degrees? So somewhere right about here. And as we've seen in the past, let's do the calculation here. Let's find the intersection. That's the first one. That's the second one. My guess, sure, good enough. And there we have it, 23 minutes. So using the calculator, let's then find the answer to the next part here. When will the temperature be 30 degrees? So 30 degrees, it's way over here. So it's going to be quite a while. So let's change this to 30. Give it some time. And then once we have the 30, we'll do the intersection like we did before. So calculate. Oh, that's almost right on top of it, isn't it? So it tells me that in about 77 minutes. Okay, so our temperature is going to be 30 degrees Celsius in about 77 minutes. All right, and there you have it. Thank you, Mr. Sir Isaac Newton, for your law of cooling. So very helpful.